Hi everyone, we're going to pick up with chapter 11 now, which is sequences and series, if you're looking at the entire chapter. And so this particular chapter usually is, as a whole, the chapter that probably makes the least amount of sense to a student just because it's so different from anything that we've ever done in any math class really before this, except for maybe like a geometry class. If you went far enough in high school, you may have seen this sort of idea. And so it's a little bit different, but we're going to try to get through it. Hopefully it's not too scary. The first section is strictly sequences, so we're going to talk about what a sequence is. So a sequence can be thought of as a list of numbers, and that's really all it is. And they have to be in a certain order. So you'll notice that we'll have A1 would be one number, A2 would be a different number, A3, A4, and just keep going ever how many numbers there are. And instead of writing it out as A1, comma A2, comma A3, comma A4, instead of writing it out like that, we'll write it in this notation down here, where you'll have A sub n being basically the formula of how you find the list of numbers. Or you might you might want to put a starting and ending point on the outside, which is what these things are on the right hand side. N starting at 1 going to infinity. That would be your starting and stopping points. And so I just put a list of different ones on here that you might see in different sections or whatever. So the first one, this one right here, the n divided by n plus 1 going from 1 to infinity. And so the a sub n part would just be the part on the inside. That's what the a sub n over n plus 1 is. If you plugged in the numbers, if you started with 1, you get 1 over 1 plus 1. That would be this 1/2 right here. If I plugged in 2, I get 2 over 2 plus 1, which would be 2/3. That would be this number. And you plug in 3, you get this one. You plug in 4, you get this one. And so on as far as you want to go. And you can do that with all of these. The next one, the second one right here, this is a alternating series. We'll talk more about that a little bit later in the chapter. Alternating series because you'll notice every other number is a negative. And then you're just, again, plugging stuff in. Now notice, there's no notation of where you're starting at on this one. And so if there's no n equals whatever to whatever on the outside, the default is that it would go from 1 to infinity. So if it's not there, that's usually what we'll go with. If you plug in 1, 1 plus 1 would be 2, so you'll get this right here when n equals 1. And then you get n equals 2, n equals 3, and so on. If it's different than starting at 1, like number 3 is, you'll definitely want to know where it starts at. So this one starts at 3 because the square root of 3 minus 3 is 0. You couldn't do n equals 2 because you get a negative number underneath the radical. And so that's why to get this list of numbers, this is what you get when you plug in 3, 4, 5, 6, and so on. And you can do it with trig functions like on this fourth example, where cosine is n pi over 6. We're starting n at 0, going to infinity. And you basically get values that were off of the unit circle, going around the circle for multiples of pi over 6. And so that's all the sequences. One of the more famous sequences is the Fibonacci sequence. So the Fibonacci sequence are the numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, and you can keep going. But basically, it is a sequence where the number coming up is dependent on the numbers before it. So you have to take the 1 plus 1 gives you the 2, or the 5 plus 8 gives you the 13. And so you take the two previous numbers to get the next number. And you just start with a pair of 1s. So 1 and 1 make 2, 1 plus 2 is 3, 3 plus 2 is 5, and work your way up. So that's a little bit different sequence. But a sequence has a limit if we're going to infinity. And just like what we talked about in Cal 1, you can write the limit as n equals, n approaches infinity of a sub n would go to L. If we try to make the terms of a sub n as close to L as we like by taking n being really, really, really large values. And if it approaches a number, we say that it is convergent, or it converges. Otherwise, it would diverge, or would be divergent. You might remember this kind of topic from the very end of Cal 2 when you did improper integrals. We talked about converging and diverging in that section. If you remember that, I think it was section 8.1 or so. And then a sequence is increasing if all of the values, a sub n, is less than a sub n plus 1 for all n greater than or equal to 1. And so in that case, basically the next term down is just bigger. The Fibonacci sequence is an increasing sequence because every term going further down the list is bigger than the previous terms. It's decreasing if it's the other way around. So if every single term gets smaller as you go down the list, and it's monotonic if it's not increasing or decreasing. And so that would be like if you had a whole list of 2s, that would be monotonic. Okay, this says list the first 5 terms of the sequence, which is not too bad. Here we are going to assume that we are starting with 1. So we're going to do what is a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. So let's start with a sub 1. A sub 1 says negative 1 to the 1 minus 1 over 5 to the 1. So that's negative 1 to the 0 over 5. Well, negative 1 to the 0 is just 1, so that's just 1/5. So our first number is 1/5. A sub 2 would be negative 1 to the 2 minus 1. You're just plugging the 2 in where the n is, and over 5 squared. So that's negative 1 to the first power over 25. Ooh, that did not look like a 25 there for a moment. Try that again. 5 squared is 25. And so negative 1 to the first power is still negative 1, so I get negative 1 over 25. If I did a sub 3, that would be negative 1 cubed, 3 minus 1, sorry, not just cubed, over 5 cubed. And so that's negative 1 squared over 125. Negative 1 squared is 1, so I get 1 over 125. And you might notice this is going to be an alternating series as well. The first term's positive, then it's negative, then the next one's positive. So the next one should probably come out to be negative. So a sub 4 would be negative 1 to the 4 minus 1 over 5 to the 4th. So that's negative 1 cubed over 625, or negative 1 over 625. And then a sub 5 for the 5th term would be negative 1 to the 5 minus 1 over 5 to the 5th. 5 minus 1 is 4. Negative 1 to the 4th would be a positive 1. And everybody knows 5 to the 5th, hopefully, is 3,125. If you don't know that, that's what a calculator would be for. And so our list would be this 1/5, negative 1 over 25, positive 1 over 125, negative 1 over 625, and positive 1 over 3125. And that would be your first 5 terms. That one is a sequence where the terms are all independent of each other. You don't need to know the first term to come up with the third term, for instance. But you could have, like in part B, that would be a recursive formula where you use some part of it to come up with the next part. And B and C are both recursive. And so they tell you a sub 1 is 1. A sub 2 would be 5 times a sub 1 minus 3, or 5 times 1 minus 3, which is 2. And so I need a sub 1 to come up with a sub 2. Same thing if I found a sub 3. A sub 3 would be 5 times a sub 2 minus 3, or 5 times 2, which is 10, minus 3, which is 7. A sub 4 would be 5 times a sub 3 minus 3, or 5 times the 7. 5 times 7 is 35, minus 3 would be 32. And then a sub 5 would be 5 times a sub 4 minus 3. So you're doing 5 times 32 minus 3. 5 times 32 is 160, minus 3 is 157. So my list here would be 1, 2, 7, 32, 157. And you might be thinking, oh, this isn't too bad at all. I could definitely do this. I will say this is the easiest section of all of them, so don't jump the gun too quick. And C works just the same way as B does. I know a sub 1 is 2, so a sub 2 would be a sub 1 over 1 plus a sub 1, or 2 over 1 plus 2, which is 2/3. A sub 3 would be a sub 2 over 1 plus a sub 2. So this one comes out not quite as nice. This is 2/3 over 1 plus 2/3. So what I would do here is multiply the entire thing by 3 on top and bottom. And that way on the top, the 2/3 times the 3 will just give you a 2 on the top. And I get 3 plus 2 on the bottom, which is 2/5. And by the way, what you'll notice is a pattern popping up on some of these, and this would be a great example of this. The first one is 2, which is really 2 divided by 1. The second one is 2 divided by 3. The third one is 2 divided by 5. So my hypothesis here would be that a sub 4 is probably going to be 2 divided by 7. And this is a sub 3 divided by 1 plus a sub 3. Sometimes the patterns don't really pop up terribly well, and it's kind of hard to see, but this one looks pretty good, because what I could do is multiply the top and the bottom by 5 in this case, and I'd get a 2 on top, and I'd get 5 plus 2 on the bottom, which is 2/7. And if you did another one, I won't go through it, but if you want to go through it, you can. The next one would be 2/9, and the next one would be 2/11, and then 2/13, and so on. So your list here would go 2, 2/3, 2/5, 2/7, and 2/9. And that would be the first first 5 terms of that sequence. Okay, this is actually going the other way around. Instead of, here's a formula, let's find the list of numbers, we're going to say, here's a list of numbers, can you find a formula to make that list come out? And so, a little bit different, but not too bad. The first one should be fairly easy. Notice that all the numbers on the top are the number 1. And so, my guess would be that I need an a sub n that strictly just has a 1 on top. If the top is always 1, the top is always 1. And so you kind of have to treat this as, okay, this is n equals 1, 2, 3, 4, 5, and so on. So to get those bottom numbers, what would you do to the n to get the bottom number? Well, hopefully you can notice that you would double them. If you double the n equals 1, you get the 2 on the bottom of the first one. If you double the n equals 2, you get 4. If you double n equals 3, you get 6. So really, the bottom is just 2 times the n that you're on. And that's it. That would be your formula. Or if you want to write it in the notation like this, from n equals 1 to infinity. either one. But the a sub n itself would be 1 over 2n. B is a little harder to notice, and sometimes it's not very useful to look at the first couple of terms. Like if you go from -3 to 2, well, there could be a lot of different ways to go from -3 to 2, but then it goes to fractions, and you look like, well, you're doing a bunch of fractions from there on out. And so it might not be quite as useful to look at the 3 and the 2, but if you see a long list of fractions, how are you going from one fraction to the other fraction? Might be easier to come up with. And so, for instance, if I was looking from here to here, what it looks like I multiplied by was a -2/3. If I go from here to here, what it looks like I multiplied by was a -2/3. And so there's probably going to be a -2/3 in the problem that's getting multiplied across. So if I kind of work my way backwards from that, if this is n equals 1 and 2 and 3 and 4 and 5, what I could do is say, well, from this first one to the second one, I could have multiplied by -2/3. And if I go from the second one to the third one, yeah, I definitely multiply by -2/3 there. So I'm going to use a sub n, and I got to come up with something to do with that -2/3. How many -2/3 are you multiplying by? Just one additional one. So I need a power of either an n on each one, or I need n minus 1 or n plus 1, something like that. And I need to figure out how do I get from from the positive 1 for the n to the -3 that I started with. And so the -3 you started with, well, the easy thing would be if I just put -3 here and do n minus 1 up top. That way when I plug in 1, n minus 1 will become 1 minus 1, which would be 0. -2/3 to the 0 power would be 1 times the -3 in front. That would give me my first one. If I plug in 2, 2 minus 1 would be 1. So I get a -2/3 to the first power, which is -2/3, times -3, which would give me 2. And you can keep checking them on and on and on and on, but this would be a formula to do that. And by the way, there may not be just one particular formula to give you the correct pattern. It could be multiple formulas. So if you see another one, you may not be wrong. And that's okay. All right, this says determine if the sequence converges or diverges, and if it does converge, we're going to go ahead and find the limit as well. This goes back exactly to what you were doing in Cal 1 when you did limits going towards infinity. All you want to do is find the limit as n goes to infinity of 3 plus 5n squared over n plus n squared. And what we did back then was you had a list of rules. You had the rule of you have a higher power on top, then what we would have said then is that either the limit didn't exist or that the limit went to infinity or negative infinity. Here what we're going to say, that's where we're going to diverge. If you have a higher power on the bottom, then that's where we're going to say it goes to 0. And so that converges to 0. And the third one, if you have the same high power on the top and the bottom, then we ended up with the ratio of the coefficients of that highest power. So in our case, on this particular problem, notice we have n squared being the highest power. We have an n squared on top, and we have an n squared on bottom. They are the same power. The highest power on the top and the bottom are the same, so our answer becomes the ratio of the coefficients in front. So we get 5 over 1, which is 5. That limit converges to 5. If we apply that same process on number 2 here, we did the limit as n goes to infinity of n to the 4th over n cubed minus 2n. On this one, 4 is the biggest power on top. 3 is the biggest power on the bottom. So your higher power is on top. That means this diverges. If you compare your powers and it's higher on the top than it is on the bottom, then we will diverge. And that's strictly from what you did back a long time ago in Cal 1. So hopefully you remember most of that. Okay, this says determine if the sequence converges or diverges, just like what we did on the last couple, and find the limit. There is a little theorem that goes along on this one that says the sequence, that if you had an R, a ratio to a power, that sequence converges if your power is between -1 and 1, including the 1, but not including the -1, and is divergent for any other value of R. And so all you're looking for here is to see if your ratio is between those two numbers, and if it is, it will converge to 0 if it's strictly between the two values. So that's what this one says. If you're strictly between -1 and 1, it goes to 0. If you're exactly equal to 1, then it goes to 1. And any other options would be divergent. So on this first problem, a sub n equals 2 plus 0.86 to the n. This part is what this theorem, this little blue box above it, is telling us about. If I found the limit as n goes to infinity of 2 plus 0.086 to the n, that little blue box says that this thing has to go to 0 because 0.86 is between -1 and 1. And so I just get 2 plus 0, which is 2. That converges to the number 2. On part B, that really doesn't apply up there. We can go back to what we were doing on the other ones, on the other page. The limit as n goes to infinity. We have an n squared. On the bottom, we have the square root of n cubed plus 4n. On the top, our highest power is this 2. On the bottom, remember, if you have a square root on there, you're not looking at the highest power being 3, but your highest power is 3/2 because of the square root. You have to take the square root, which would be dividing the power by 2. And so 3/2 is actually less than 2. So the higher power is on top. So we are, on this case, higher on top. So this thing has to diverge. And that's it. That's all we're going to do in this particular section. So hopefully that's pretty easy. And we will pick up with 11.2 in the next section.